Hey everybody, and welcome to Chapter 4. So this episode is all about perceiving objects. I like to think of this as easier than Chapters 3 and 5, and I've kind of talked about that a little bit before, I know. But I feel like this, for me at least, is a little bit easier to wrap my head around than the spatial frequencies and all those kinds of nitty-gritty things that we talked about in Chapter 3. So now this is where we are going to start putting together all of those lines. So if Chapter 3 was all about how we kind of detect edges and lines, now we're going to take those lines, those contours, those edges, those spatial frequencies, and we're going to look at basically how they are organized, how they come together to form objects. Alright, so let's get into it. So most of what we're going to be talking about today in these videos is going to be the what versus where pathway. That's going to be one video. We're going to have one video for middle vision, and then we'll have another video for what they call recognition by components, and then finally we will have a face perception video that walks through a little bit about what it's like to perceive things, both objects and faces, in the brain. So alright, let's get into it. You'll see these videos that are posted here, especially this first one. If you check out any of these three, I think they're all worth watching. This top one right here, though, this one focuses on visual agnosia, which is something that we're going to refer to several times today. So go ahead and bookmark it, or if you want to, you can watch it right now. But it's 5 minutes long, very, very interesting, and we'll talk more about it in just a moment. Alright, so as I mentioned, last chapter was all about how we detect lines, and so when we're detecting things, even like words, you can see that it's, that this T, for example, that this T is two lines, right? But we don't really perceive it as two lines. We perceive it as a letter, because we have seen this combination of lines several times before, right? So whenever we see all of these different lines, we don't really perceive them as lines, we perceive them as letters, and we perceive those letters as words, and those words as something that carries meaning. So how does this happen? That's what we're looking at this chapter. Last we left off in Chapter 3, we were talking a lot about the striate cortex and the V1, that primary visual cortex. Now we're going to be moving a little bit farther down the stream in the brain. We'll be talking about the extrastriate cortex, which I feel like is not a very descriptive way of talking about what it is. Instead, usually I'm going to refer to it as either the secondary visual cortex or V2, V3, V4, V5, and V6. They all mean the same thing. But these are the areas that we're really going to be focusing on, because this is where some of the magic starts to happen, when we start combining these features together. But before we really get into that discussion, I want to spend a little bit of time talking about how the brain is organized. The way the brain is organized, as we know, super complicated, right? But one of the things that I think is really fascinating about the brain, or about at least how we perceive anything, is, for example, if I were to ask you, what is this that I'm holding in my hand, you'd be able to tell me that it's a cup of coffee, right? But whenever you're doing that, what your brain is processing is, well, it's processing several different things, but there's two primary things that it's processing. It's processing what this is, but it's also processing where it is. That may not come as a surprise. But what is a surprise is that these two processes are completely different. They don't even really interact with one another. So whenever we are looking at an object, we have one part of our brain that's going to tell us where something is, and we have one part of our brain that's going to tell us what something is. So this is known as the what versus where pathway. That where information is going to go up basically to the top of the head, to the dorsal pathway, which you can see right here. That stream is going to go from the occipital lobe to the parietal lobe, and on the other hand, the identity of an object is going to go underneath. It's going to go from the occipital lobe to the temporal lobe. So this is a big simplification, because again, the brain is very, very complex, but we're not really going to mention any of the exceptions here, because they're very, very rare. If you want to know more about the exceptions, you can learn about it in grad school if you decide to go into like a neuroscience degree, but otherwise, for the most part, most of our day-to-day perception is like this. That what something is going to be processed in one part of the brain, where something is going to be processed in a different part of the brain. So, as I mentioned, that was a very as a simplified version of the matter, because this is kind of a closer look of what actually is going on here. And you can see that down in here we have the lateral geniculate nucleus with the magnocellular and the parvocellular layers. And you can see how it feeds into the V1 up here, and then it just kind of explodes, and information goes in all these different circuits, all these different pathways. It gets very, very complicated. But ultimately, what you'll see is that, again, the location of an object is going to be processed in this stream up here, and what something is going to be processed down here. I tried to play a little bit of a joke on my in-class section, and I pulled this figure up, and I said, all right, this schematic right here, I'm going to expect you to be able to label that for the exam. And they got very, very quiet, and then when I said, yeah, I'm just joking, you don't actually have to do that, there was maybe one or two people who had some nervous laughter, but for the most part, people did not think that it's funny. But again, if you want to know more about that stuff, that's beyond kind of the undergraduate level that we are going to be learning about this semester. Alright, so talking a little bit more about the what pathway, that pathway down there at the bottom, the primary anatomical structure that we are going to concern ourselves with is the inferotemporal cortex, oftentimes just simply abbreviated as the IT cortex. And the IT cortex is going to do a lot of the heavy lifting for common object recognition. So, you may ask, how do we know that? How do we know a lot of this stuff? A lot of the stuff we know because of lesion studies. And we've talked about this a little bit already this semester, but a lot of what we know comes to us because we have seen what happens whenever parts of the brain have been damaged in some way. We can look at how behavior differs or how perception differs after that brain has been damaged. So, excuse me. So, a lot of this in particular has been looking at people who have damaged this part of their brain and now they cannot recognize what objects are. So that has told us a lot about the what pathway. Moving on, this is the video that I referenced at the very beginning. This is an example of visual agnosia. Definitely check it out. It's about this adult who got into a car accident and destroyed this part of his brain, and because of that he can no longer recognize common objects. He would not be able to tell me what this is in my hand. He would not be able to tell me what this is, or even what it says. This lecture, by the way, is brought to you by Dunkin' Donuts and Burt's Bees lip balm. But he would not be able to recognize what those are. He can recognize, however, what the colors of them are, what the basic outlines are, maybe, and also where they are. And so that tells us that whenever the inferotemporal cortex is impaired or compromised in some way, that it hinders our ability to recognize objects, but does not kind of impair our ability to know where things are in our environment, or even what color they are, because they are handled by different parts of the brain. Alright, so moving on a little bit, I'm going to get you to do a quick mental exercise. I want you to, as quickly as you can, think about what it is that I'm going to show you. So in other words, think about what the picture is. So if it's a picture of a cup, I want you to think cup. You don't have to be specific, you can be broad, you can be general. But I want you to think about how quickly you're able to do it. Alright, so here's the first one. Here's the second one. Here's the third one. And here's the fourth one. So yes, all of these are houses, right? And if you were kind of keeping track of how quickly you're able to do that, you recognize that you were able to classify those objects very, very quickly, right? And that's because object recognition happens very, very quickly. We don't have to spend a lot of time thinking about what it is that we are looking at. Which again, if you think about all the different processes that have led up to this point, that we have light entering the eye, we have the retinal cells that are transducing this energy into action potentials, we have that traveling through the lateral geniculate nucleus to the V1, where it's going to be handled by these different receptive fields and the simple cortical cells and all this other stuff. That all this is happening in the blink of an eye, that it's happening that quickly. So yeah, we recognize that these are all houses. The fascinating thing to me is that, like if you look at A and B, those are the same houses. But we recognize them both as houses, even though they are at different angles, We also recognize these two down here to be houses as well, even though they are different. One of them it looks similar. It's got a chimney, it's got a little porch and all that stuff. The other one is a completely different medium, right? That's a painting, where this is a photograph. This is an example of not only how quickly we can classify and recognize what objects are, but how broad that process is. What we're doing is going to be looking for these common features that all of these different instantiations of this object have. So when we are depicting a house, we're doing this as quickly as about 150 milliseconds. Very, very fast. And what that means is that it's essentially so fast that it doesn't even have to recruit the higher order brain areas. What does that mean? Basically, the frontal lobe, the prefrontal cortex, these areas that are mostly kind of responsible for detecting or handling complex thought, complex cognition, logic and reasoning and creativity and planning and all these more quote-unquote human behaviors, these cognitive kind of behaviors, that we don't even need all that. That a lot of this processing is going to be happening in the temporal lobe. That this is all going to be happening in the lower order functions, the deep brain functions. So whenever we are detecting this stuff, we might perceive this house, but what we are actually detecting is going to be the individual features that make up this house. And then we're going to recognize what those individual features are, put them together, and then recognize, oh yeah, that is a house because other houses that I have seen have these same kinds of features, broadly speaking. So this is a cool example of sensation versus perception, where here on the right, we're looking at what our eyes are detecting. Our eyes aren't really detecting a house per se. Instead, they are detecting the contours that make up this house. But what we perceive is going to be all the stuff added together, where then we perceive it as a house. So our detection is different from our perception. Why is that? I'll tell you a little bit more about that in the next video. See you soon. Bye.